So, hello everybody, thanks a lot for being here. So the first speaker is Paolo Peron. He's a research associate at the University of Oxford. He did his PhD under the supervision of Professor Jost. I don't know if I pronounced it correctly, but Jost, okay. His interests are in categorical probability and information theory and reformulating classical results like definity theorem and ergodic decomposition theorem in a categorical setting. He will present us his work on categorical information geometry.
Thank you. Thank you. Thanks to the organizer for the conference in this impressive, amazing location. Let's get started. So what I'm doing here, I usually come from trying to get probability and category theory to talk to one another. For historical reason, there's not much research on that yet, but there's no mathematical obstacle to that. It's just that it hasn't happened historically. And in working with that, we discovered that information theory also fits the picture very well. Maybe a question to keep in mind is a lot of things in information theory are distances from some case. Think of mutual information. It's something like a distance to product measures. What is entropy? The distance to, though. Okay? And this work basically answers that in many cases. So let's get through that. First of all, let me use a graphical formalism. Differently from the paper, I will go up for reasons of space, so the more things fit in a slide. I will not explain what a category is. Just imagine you have a bunch of devices and cables you can connect together, but cables are of different kind, right? You cannot insert a USB port into, USB-C port. Same thing here. So imagine states are these wires that go up, and these are, imagine a cable that have many possible signals that they can go, and of course, outputs and inputs will select some particular thing that can be transmitted in this cable. So these are spaces of possible states. The blocks, which go from bottom to top, are transitions which have some randomness, okay? So given some input here, some output will be transmitted, usually in a random way. You can connect them and compose them vertically. And then we also have what we call the monoidal unit, which is like the no input channel. So imagine something that produces an output without needing any input, a source in information theory, okay? Think of probability measures that are transitions from no information to something. They are not conditional. All right, so many things are examples of this. The most easy thing to keep in mind is the category called Finstock. Objects are finite sets, and morphisms are stochastic matrices between them, which are matrices of non-negative entries such that the sum over the columns is 1. So you can view these as conditional probabilities. And you compose them with the usual formula, Chapman-Kolmogorov equation, which tells you that the second transitions are independent from the first, just like in a Markov process. Hence the name. But Markov categories are not just made to model Markov processes, they model all processes. The Markov ones are the simplest ones, or they are the easiest one to write. They are kind of the basic case. All right? And you can see here a probability distribution, in this case finite, is one that doesn't depend on anything, so these are just column vectors. So states from the monoidal unit. This is not limited to the discrete case. You can do exactly the same with integrals instead of sum, and it works exactly the same way. But for the purposes of this talk, I will focus on the finite case. There is the infinite case. There's also a lot more exotic examples. This formalism is very general, but maybe at the end I'll give you some references where to look at the more general case. All right, so probability is not just about spaces of measures, right? It's mostly about how different random variables interact and allow you to make predictions. So here's an idea. We don't just have sequential composition of channels, but also parallel, which works as follows. You have a way of forming products of the states, of the spaces of states, and then a general channel between them is in this form. But whenever you have a channel, say from X to Y and one from Z to W, then you can compose them and form a particular channel that is non-signaling, like it can be split here. So here you see Y does not depend on Z and so on. For states, that's exactly forming product measures out of all possible joints. So in here, in general, you have that knowing something about X, say, could tell you something about Y. They're random, but you can do inference. Here, instead, it will tell you nothing, like in a product measure. How do you still say that, for example, this is a joint distribution of these two and not just an arbitrary joint? You have to marginalize. So we need this map which corresponds to something like summing over the columns or integrating, marginalizing. We call it a discard map, and forming a marginal means applying that map to one of those outputs. And it goes to nothing, so to the monoidal unit again. This condition tells us that integrating before or after is the same thing, which is the same thing as saying probabilities are normalized, or columns sum to 1. Or you could view this as saying that if you have some input, process it, and discard the output, it's the same thing as discarding the input to begin with. So you can interpret this as probability or as information theory. All right, so here's the definition. A Markov category is what's called a symmetric monoidal category. So category, sequential composition, monoidal, parallel composition, symmetric, you can exchange the things. Semi-Cartesian, meaning that these maps, there's only one of these maps that discard stuff. With these two maps, copy and discard, satisfying the actions of a commutative comonoid. Now, you know category theories like putting co and reversing arrows. What is a monoid? You know, right? Like a semigroup. That's associative. You see this is like associativity if you go from up to down. This is co-associativity. You go from down to up. What does it mean? It basically means that these things have a good interpretation as copy and discard. For example, this one tells you that if you copy and then copy one of the two copies, it's the same thing as copying the other copy. You just have 3 equal copies. This one tells you that copying and discarding one of the copies is the same as doing nothing, and this that the 2 copies are exchangeable. Okay? Now, that's the definition of Markov category. What can we do with that? Okay, first of all, we can define stochastic independence in general. So a joint state here is the product of its marginals if and only if you say that this thing denotes independence. And if you instantiate this for Finstock, that gives you exactly that are those probabilities which are the products of probability. More general, for channels, again, a channel with 2 outputs exhibits conditional independence given input if pretty much the same equation holds. Here's where we use the copy map. If you look at this equation, we have to use A twice, and it's the same A. It's not A and A prime. So we had to copy the value of A. That's where it comes in here, okay? And again, you see, it's nice because if you know about graphical models, you know that like separations, like d-separation, for example, for graphical models, is something like telling you graphically in a topological way, so to say, whether things are stochastically dependent or independent. Here's the same, except that there's no d-separation. It's just separation, a little bit like in Markov random fields. So you can actually prove that a certain configuration gives you conditional independence, even only if you can split it in some way, like as in here. More importantly, which one of these are deterministic? Well, for states, this tells you that basically take a state and copy. If this has like, let me say, self-independence, like if something is independent of itself copied, then you call it deterministic. You can do the math for the case of Finstock. That gives you exactly those, well, probability distributions, which are just zeros or ones. So for which you know exactly which events are going to happen and which ones are not. In the standard REL case, those are exactly just the points. More general, you have conditional determinism. Again, it's exactly those stochastic matrices that just have 0 and 1 transitions, so the ones that are not really random. You can do the math. And it has this additional interpretation of, well, you see here, if f is a process that contains some randomness, say adding to A the value of, I don't know, a die roll, then rolling your die and then copying the result is going to give something random but perfectly correlated here, given the input. Why here, you see that you're rolling the die twice. And so out here you'll get something that's perfectly independent, or at least conditionally independent given the input. Okay? So these, if f is just a function, in both cases you get f of a, like a tuple. But if it has randomness, the correlations are going to be different. And you can take this as definition of randomness. I can prove that randomness is exactly when 2 things differ. I also like saying that this famous quote by Einstein that says, madness is doing the same thing twice and expecting different results. I cannot judge madness, I'm not a psychiatrist, but I think that's rather an excellent definition of randomness. Randomness is exactly doing the same thing twice and expecting different results, right? And that's exactly how we're defining it here. We're doing f twice and expecting the same result. All right, so we can take this as definition and it recovers the usual probabilistic thing. when it fails. We can do a lot of probability theory just by writing down string diagrams and manipulating them, proving theorems of probability theory just categorically. I think the most important one is Definetti, which is one of the big ones, but there's many more. And now the question is, all right, can we do information theory? And the answer is yes, we can. At least so far we were able to do quite a few things. What's the difference with probability is that in probability theory, things are independent or dependent, but you don't have a measure of how much they are dependent, say. In information theory, instead, you want numbers. You want to say that two things are the same, how can I say? You want to say that two things are not just independent, but you want to measure the departure from it. And so the usual category theory is not suited for that, because category theory, either a diagram commutes or not. Like two things are equal or not, and there are no numbers. It's very qualitative. But we can enrich these categories and put numbers in it in a standard way. And it turns out that information theory is exactly what you get out of that, at least in the finite case. So let's do that. Take a Markov category. A divergence on it is a divergence on the arrows, on the hum set, on the processes. Okay? Which has to satisfy these two conditions. So first one says that if you do parallel composition, then the divergence between the compositions is less or equal than the one between the components. And the second one is the same thing for parallel composition. Okay, so in particular you see that if G equals G prime, this is a sort of data processing inequality that tells you that if these two things have some distance and you process them in the same way, then the distance is not going to increase. Okay? Now, since we all saw this beautiful talk this morning, this is not saying that chaos theory is false or not considered. It is. These are the distributions. So this is not saying that the single trajectories never diverge more than they do in the beginning, but that the distributions overall, the laws, are bounded by equal processing. Okay? It's like a, Langevin versus Molokowski picture, kind of. The densities here don't get too far. And these two equations are the basis of a lot of things in information theory. And if it's not clear immediately, let me walk you through that in a moment. From a theoretical perspective, this is saying that we are enriching our category in a category that looks a lot like the one of metric spaces, except that we don't want the triangle inequality. Also keep in mind, these look like triangle inequalities, but they're not. This is not making the divergence a metric. They are like triangles in different places, so to say. And this category is the one that makes the whole thing work. So you can rewrite the previous definition simply by saying our Markov category is monoidally enriched in this. For the non-categorically minded, here's a much more practical explanation of that thing. Form any configurations of blocks. Here I put 3, but you can put 1,000,000. No matter how complicated. And do pattern matching in any way so that they look like the same configurations, but they might have even a more internal structure than this. Well, then the divergence between the big configurations is always bounded by the sum of each part. And that's, of course, they don't always match exactly, right? But for any way you can do partial pattern matching, you get a bound for each pattern matching that you can do. So it's a little bit like the whole is more than the sum of its parts, but the distance between the wholes is less than the distance. It's less than the sum of the distances of the parts. Something like approximate compositionality. Okay? And that's equivalent to the inequalities we saw before. There are further equivalent characterizations. This is one that is in terms of joints and marginals. And it's particularly nice whenever we define the distances or divergences between channels as just the distances between states and then taking the supremum or maximum of the inputs, because then it just becomes like this. And these are particularly convenient for us, because the first one tells us that the divergence between the marginals is less than the divergence between the joints. In other words, that the divergence is monotone in the number of variables observed, just like entropy. And the second one is telling us that if we form a joint by a marginal and a conditional, then the distance is bounded by the one between the marginal and the one between the conditionals. So that's basically, I want to say, a tropical looking version of a chain rule with an inequality. So if in the usual chain rule here, instead of a sub, you have a convex combination, and here an inequality. But this in particular is implied by the usual chain rule of entropy. But it's more general. Using this, so these are the two equations that will make our Markov category enriched in divergences. And these can be very easily checked on classical examples. We did that, and you can prove that the KL divergence is a divergence of Finstock. That's for states, and for channels, you just take the maximum over the input. Same thing for the Rényi divergence, and here's why you need the more general chain rule and not the usual one, because you probably know that only KL satisfies the usual chain rule. And even other metrics on spaces of probability measures do the trick, like the total variation distance, for example, does. Okay, a metric is a divergence. So these are all giving us enrichments on Finstock. You can also do it for infinite case using integrals. I'm not going to do it in this talk, but you can. All right, so remember that we said that P that exhibits independence if and only if these two things are equal. Then, all right, we define the mutual information exactly as a divergence between these two. So it's 0 if these are independent. And, well, if you do this for these three examples of divergences that I gave you, you get exactly the usual examples, like Shannon mutual information, Rényi mutual information, and the version that's kind of total variation in flavor that I've never seen before, but does the same job. And most people in information theory actually define mutual information this way. So it's not like I'm reinventing mutual information. That's what people did all along. Okay? But for entropy, the situation is a little bit more interesting. Remember that P is deterministic if and only if this equation holds. And you can do the math. You can define entropy as exactly the divergence between these two. And you get exactly Shannon's entropy without any factors to simplify, anything to subtract. You can do the math, and Shannon entropy is exactly the divergence between this and this. So the two things that are equal in Markov categories, if and only if they are equal. If and only if we have determinism. So for mutual information, we kind of knew it was some kind of distance. For entropy, some people take it as a distance to the like uniform case, but then you have some correction terms. Instead, if you do this, everything just works on the nose. So one could say entropy in the finite case is, so to say, the distance between these two things. And so for the Rényi mutual information, interestingly, we don't quite get Rényi entropy. We do, but of a different order. So for the divergence of order alpha, we get the entropy of order 2 minus alpha, which has the same interpretation, but it's not the same. Of course, you probably know that for alpha tending to 1, that's just KL. And so it all works out because 2 minus 1 is 1. So it's something like there's a reflection happening there. For the total variation distance, you get this quantity, which have been rediscovered a lot of times. So in ecology and in diversity, they call it the Gini-Simpson coefficient. Just like entropy, it's a measure of like how spread something is. Also in the quantum case, so if instead of sums, you get like traces of density matrix and so on. That's called a linear entropy, because I guess it's kind of like entropy, except that instead of the logarithm, you have this linearization of it. And it has been rediscovered multiple times, but that also does the same job as quantifying diversity of or randomness. These are all special cases of the same thing. Okay. Here are they. So you see, for example, for the uniform measure on 2 elements, all these things are maximum. 1 if you choose logarithm in base 2, and they're 0 on the deterministic measures. But how steep they are changes. So Shannon entropy is like the most harmonic looking one. The other ones are like more vertical or less, and for alpha larger than 2, it even fails to be concave. Here it does a little bit like this. The Gini-Simpson coefficient is asymptotic to alpha equals square root of 2, but it's not the same. It's just like a Taylor expansion of it. But you see, these all work in the same way, and these can be seen all as maximizing randomness in some way. Okay? As I said before, these inequalities we have as corollaries a bunch of data processing inequalities for all these measures. So for divergences, this tells us that if you process two things in the same way, then their distance cannot increase. Again, this is not violating chaos theory. This is about distributions, not single trajectories. And that the divergence, observing more random variables will give you more distinctions, not less. For mutual information, it's the same. This tells you that, for example, processing independent random variables independently is going to keep them independent, which you know in traditional probability theory, but this framework is general, so it has nothing to do with like real numbers. This is just a categorical statement. And just as well, that things can only be more independent if you see less of them. And for entropy, also the same thing. Like if you have now F deterministic, of course, if F adds randomness, anything can happen. But if you process deterministically some random variables, then the randomness can only decrease. Okay? And in particular, you can take F to be marginalization, so you got that joint entropy is always more or equal than marginal entropy. Again, these are not proven using the Shannon inequalities. These are just following from the categorical framework, and this holds in particular for Renyi, for the total variation distance, or if you come up with any other divergence on any Markov category, these equations will still hold automatically. So they're like, in some sense, more fundamental. They're like the usual Shannon ones are instances of these. All right, I think I'm almost going to stop. Let me just say, this is just one step. I think there's a lot more to do. And here are some open problems that I would even like to pose you if anybody has ideas and wants to try to do this with or without me. The first one is, what about the continuous case? You can do a lot of things there, but one thing you cannot do is, for example, include differential entropy. One reason is that, well, take a Dirac delta, which should be like a deterministic one. That does not have differential entropy 0. It has differential entropy negative infinity. So that's not an instance of anything from anything, because it's a negative number. But even if you like add infinity to that in some way, you still get, like, there's a deeper problem, because take, for example, Gaussians on the real line of different variances. Okay? Those have different differential entropies. However, as measure spaces, those are isomorphic, because rescaling is an isomorphism of measure spaces. Measurable structures are blind to the geometry, right? So the differential entropy, if it is a divergence on some category, it's not on the category of measurable spaces and Markov kernels. But it's a divergence on something that is more sensitive to the geometry. It's like it's a finer invariant than just an invariant of measurable spaces. What is it? I don't know. Another thing is that category theory gives you universal properties, and rich category theory gives you universal properties up to epsilon. So there are a lot of universal properties coming up in probability, say Kolmogorov's extension theorem, which is about like a filter co-limit of things, or co-filtered limit if you reverse the arrows. Can you do all that up to epsilon? I believe so, but we still haven't done it. But I think there's a lot of work to do there. And maybe the most interesting one for this particular conference. So far, I just gave divergences from very simple configurations, such as product measures or like copying and stuff like that. There's a lot more to that, right? In information geometry, you can take arbitrary exponential families. You can take divergences from like all sorts of families. There's like E families, M families, and so on. Can we do that categorically too? Again, I believe so, but we haven't done it. So I think there is quite an amount of work that one could do there too, and generalizing all the things that I said during this talk. I think I'm going to stop here. You can find more in the book of this conference, and if you're interested in the continuous case, it has a bunch of measured theory, but the concepts are the same, and you can find that here in this preprint. Thanks for your attention.
Hi, thank you for the talk. Have you heard of the work from Bob Koger? Yes. Yeah, so my question is, how does those Markov categories relate to the quantum mechanics framework from Bob Koger?
Yes, great question. They don't relate directly, but they were largely inspired by what they did for the quantum case. Right now, actually, we are working on merging the two formalism, or at least getting them to talk to one another. There are a lot of similarities, but not formal, but we're working on that. But definitely, we were very much inspired by what they did for quantum.
Thank you for the talk. I have a short question. I had a similar case for algebras where they abstracted to car linear categories, and so there's also a way from coming from algebra to car linear categories and also back way. So just where the morphisms are the elements and the multiplication is the composition. So and then we have such a one-to-one relation thing. What is here in the Markov categories case? Can you boil down to some sets with extra structure? Did you look there, and what kind of extra structure did you get? I assume you take the morphisms again, and the multiplication is the composition. Do you end up with a topological algebra or an algebra with a pseudometric? And what about looking at extending it to C-star algebras, because that what you were calling looking for sounds like you need some distribution theory from functional analysis. So it's worth to look at C-star algebras or stuff like that. So the question is, can you boil down the Markov category to a set with some algebraic structure?
Thanks for the question. That's an excellent question. We are trying to do that, especially with sister algebras. There is one major impediment in that the tensor product of sister algebras is notoriously complicated, and that doesn't make it a monoidal category. We have some ideas on how to get around it, but the technicalities are like exploding. So I wish I could tell you the final answer, but we're still working on it. But yeah, that's definitely something that one wants to do. Thank you.